All right, so I want to go through a few examples. These are, I did pull these from the exercises at the end of section 13.3, but they're not exercises I've assigned. So I'll go through these examples, and then you can work on some other examples on the homework. As I go through these, the goal is to construct FSA, which stands for Finite State Automata. Right? Construct finite state automata with binary input, meaning we're just using 0 and 1 as our input alphabet. This means we're dealing with bit strings for each of the specified languages. There's 3, so if you want to stop and work on all 3 of these, you can. I'll turn the page over and you can see the third one. So let's go through them first. First, we want to make an automaton that recognizes the set of all bit strings that begin with 0, 1. Okay, so as long as it starts with 0, 1, it can be anything after that. That's what we want. The second one is the set of all bit strings that do not contain 3 consecutive zeros. So as long as there's no 3 consecutive zeros, then it would be fine. Otherwise, if it has 3 consecutive 0, it is out. So those are the first 2. And then the third one we're going to do is the set of all bit strings that start and end with 1, 1. So there can be overlap there, by the way, for that one. So like 1, 1 itself, if you just take the string 1, 1, that counts because it's got 1, 1 at the beginning and it's got 1, 1 at the end. Likewise, 1, 1, 1, 3 ones, that also counts because even though there's a bit of overlap, like 1, 1, 1, 1, that still counts. All right, so just clarifying that. So if you want to pause the video now and try these on your own, I highly recommend that. I'm going to flip back over and go through these now. Okay, so the first one, set of all bit strings that begin with a 0, 1. All right, well, we need to have a starting state at 0. I'm going to be, by the way, I'm going to be just drawing the state diagram. The state diagram contains all of the information. You can see clearly what all the states are, as well as what else is going on. So I think that will suffice. But you can also, of course, build a state table if you prefer, and that would be fine. So we have a starting state at 0, and then what we need to do is start building our machine to check to see if the input string has 0, 1. Now, one thing we can say right away is that if the input string starts with a 1, then it's right out immediately, right? So the first thing I'm going to do is I'm going to make an arrow here that says if you receive a 1, starting from your starting state at 0, we're going to go to some state over here, which I'm going to refer to as the pit of despair. It is a state from whence there is no return, and it is not an accepting state. So in order to make that happen, I'm going to put 2 loops on this state, state 1, saying if you have a 0 or a 1, you just stay there. So this is now essentially a dead end. If you receive a 1 immediately at the beginning of your string, it's definitely not going to be in this language, and so it goes to the pit of despair. Sound good? All right. Now that's not an accepting state. If I made that an accepting state, then it would be a little different. We'll get to that in a moment. Okay, so if instead my first bit that I receive is a 0, then there's a chance for that string. So we're going to move to another state. I'll call this one state 2. As long as they're all get different names, then it's fine. It doesn't really matter what they're called. So I'm saying if I receive a 0, I'm going to go to this state called state 2. And there's a chance that this string might start with 0, 1, right? In particular, if the next, well, okay, I was going to say in particular, if the next bit is a 1, then the answer is yes, right? But before we get to that, let's look at the other option, the other pit of despair option, which is if it's 0, 0, right? If it's 0, 0, then again, we don't match, and the string is definitely a no. So in that case, we're receiving a 0. I'm going to send my bit string to the pit of despair again. And the answer is no for sure, no matter what follows, right? All right, so I've got that dealt with. Now the other option here is if I receive the 1, and that's the case in which I say yes. If I receive the 0 and then the 1, then yes, for sure, this string is in the language. So this new state that I transition to, state 3, I'm going to make that my accepting state. That makes it sound like there can only be one, but that's not true. There can be as many accepting states as you want. But in this case, there's only one. Because at this point, now that I've received my 0, 1, I know for sure that it's going to be in the language. So it doesn't matter what I get after the 0, 1. I'm going to stay in that accepting state. So I can loop on this with a 0 and a 1 like that. And that's it. That's the whole machine. Right? So as you can see here, if I receive the 0, 1 right away, then I end up in this, which is sort of the opposite of a pit of despair. A mountain of hope, I guess. So I end up over here, which means, yes, the bit string is in the language, and it doesn't matter what I receive after that. I'm going to stay right here and say, yes, 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 it is. Otherwise, if I receive anything else, like a 0, 0 or a 1 at the beginning, then I go to my pit of despair, and the answer is no, 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 no. No matter what you get, it's no. So this example demonstrates those two concepts, the pit of despair and the mountain of hope, which are kind of useful things to put in your machine. So that's the first one. Let's do the second one. Set of all bit strings that do not contain 3 consecutive zeros. All right, so got my starting state. That's 0. Now, my starting state actually is where I would end if I received the empty string, lambda. And the empty string, does it not contain 3 consecutive zeros? Sure. The empty string does not contain 3 consecutive zeros. So if the empty string is in the language, then I can make my starting state an accepting state. This is a if and only if. Basically, you could say the starting state is accepting if and only if lambda is in the language. All right, those are sort of equivalent to each other. And so I'm going to have that. And now if I start receiving 1s, if I begin by receiving 1s, I don't care, right? Because all I care about is making sure that we do not contain the 3 consecutive zeros. So since I don't care, I can loop and stay where I am. Right? If I receive some 1s, no matter how many I receive, I'll just loop. I'll just stay here and loop on S0 and say yes, yes, yes. I'm still accepting, right? Because S0 is accepting. Until I receive a 0. Now, if I receive a 0, then I have to pay attention to that. We have to essentially take note of the fact that we've received 1, 0. So I'm going to transition to a new state. That's how state machines keep track of information, basically. They keep track by transitioning to new states. So I take note of the fact that I've received a 0 by going to state 1. Now, in state 1, it's still accepting because I've only received a single 0 so far, right? Now, what I'm looking for is I'm looking for consecutive zeros. So if after receiving this 0, if I receive a 1, it's like a combo breaker, and you go back to where you started, right? You reset back to the first initial state. So receiving a 1 breaks the chain, and I reset back to S0. But if after receiving that 0, I received a second 0, then I would have to take note of that by moving to yet a new state. Now, this state should still be accepting because this is the point at which I've received 2 consecutive zeros. Right? But the machine is getting really nervous now because the machine's like, oh no, if I receive 1 more 0, then I go to the pit of despair, which sounds terrible. But if I receive a 1, then whew, it's okay. It's okay. We get to reset back to the beginning again, right? But the 0, 0, 0, 0, third 0 is the spell of doom. And now we go to the pit of despair from whence we never return because this string now has 3 consecutive zeros. And so no matter what occurs after that, it's going to not be in this language anymore. Okay? So there's the machine that generates or recognizes the set of all bit strings that do not contain 3 consecutive zeros. Okay. Now let's do the next one. All right, so now we want the set of all bit strings that start and end with 1, 1. So we're going to need some part of our string that's going to check to see if it starts with a 1, 1. Clearly, if I begin with a 0, then I'm going to go to a pit of despair and say no. But if I get a 1, 1, then there's a chance, and we might be able to continue. But But if I receive some zeros later on, then I'm going to have to say like, well, so far this string does not meet the requirements. It's not in the language. But you never know if you could get another 1-1 at the end later on. So there's going to be sort of a looping, cycling sort of structure to this machine where there's a chance that I can be in an accepting state and then receive some zeros and go away from that accepting state, but then receive 2 1s and come back to the accepting state. Because you never know when the bit string is going to end. There's nothing telling us, there's nothing, as far as the machine is aware, there's nothing to tell you how many bits are going to come at it, right? It's just got to keep accepting those bits and keep kind of updating its information and changing from state to state until the bits stop coming. Let's go for it. So state 0, or starting state, it should not be an accepting state because the lambda empty string does not start and end with a 1-1, right? Okay, so first and foremost, if I receive a 0 at the beginning of my string, then the answer is definitely going to be no. That's not in the language, so I will create a pit of despair over here, and I'll go to that pit when I receive the 0. But if I start with a 1, there's a chance, right? If I receive a 1, then there's a chance, and I'll represent that by going to a new state. However, if after that 1 I receive another 0, then we're done, right? So another 0 would send us back to the pit. But if the second bit is a 1, then actually we have the string 1-1, which is going to take us to a new state over here. And this state should be an accepting state because the 1-1 string itself is accepted, right? It begins with 1-1 and it also ends with 1-1. Remember I mentioned before about overlapping. If the first 2 bits happen to also be the last 2 bits, then, well, that's fine. Furthermore, if I continue to receive 1s while I am in this accepting state, then the last 2 bits are still 1, and so I'm still going to accept. So when I'm in the accepting state where my last 2 bits and first 2 bits are both 1, if I receive further 1s, I'm just going to loop. Right? I can stay right there. This is going to be the only accepting state in this machine. Now that I've established that I start with 1-1, whenever I am ending with 1-1, I'm going to make sure that I come back to this state 3. But from this state, we might receive something like a 0. So let's say I receive a 0. I'm going to say, well, at the moment, so far, this bit string does not end with a 1-1. It ends with a 0. So I'm going to go to this state over here. I'll call it state 4, which is not accepting. It's not a pit of despair, though, because you never know. I might get a 1-1 later on and bring me back over here. So from this state 4, if I receive further 0s, it doesn't really matter. I can essentially ignore them. So I'll loop and stay in the same state. But if I receive a 1 at this point, then that is meaningful because it means I might be on the way to receiving a 1-1. However, I'm not there yet. So I'm going to go over here to a state 5. Still not accepting, but I'm taking note of the fact that I've received a single 1. Now they have to be consecutive, right? So if after I get that 1, if I receive another 0, then that 1 was meaningless, right? So in that case, I'm actually going to go back to my state 4. State 4 is like what's the right word? It's like a holding pattern. You're just sitting there being like, okay, I've got zeros. I received a 1. Oh, is it going to be a 1-1? You receive a 0? Nah, it's not. Okay, go back to the holding pattern. If you receive a 1 and then a second 1, pow! That takes us back to our accepting state because the 1-1 in consecutive, if that's the last 2 bits, then that meets the pattern. But then from that accepting state, you can still go back to the holding pattern if you receive further zeros. And if you look through this machine now, I think that's it. I think we've got all of the required arrows. Remember that every state needs to have a 0 arrow and a 1 arrow leaving it. And we have that now. There we are. We've covered all of the different possible cases and situations, and our machine here is going to recognize all bit strings that start with 1-1 and also end with a 1-1. So there we go. I hope that this has shown you, I hope these examples have illustrated how to go about designing a finite automaton to recognize a specified language, at least for bit strings. You could do the same thing with other types of strings. In fact, essentially a compiler is one of these that just has lots and lots of different possible input characters and lots of complicated structures to recognize all the complicated syntax of C++ or any other programming language, whether it's Python or Perl or whatever. So yeah, that's it for this video.